All right, hello, professor and class. My name is Tony, your fellow classmate, and today I'm going to go over the journal article Implementation of Machine Learning Classification in Remote Sensing and applied and reviewed by Aaron E. Maxwell, Timothy A. Warner, and Fang Fang. And I will go over the sections from 3.3 to 5.3, which will be pages 8 to 15, and it will cover topics such as the remaining classifications from part 1 presentation, the best classification for researchers, and training data. Since the article itself is very technical, I'll try my best to simplify and explain the content. Also, in order for this presentation to make more sense, please watch the previous presentation, which is part 1 that goes over section 1. Actually, section 1 to 3.2, which is page 1 to page 8. So here are 3 keywords and concepts we need to go over it before getting into the article. Once we're familiar with these terms, it will be easier to understand the content, and we are going to start on the right side, classifications. So as we can see, it is the yellow icon here. So what is classification? Classification is one of the main functions for machine learning. It automatically put and predict data into the correct group based on the training data and sample. It's an excellent tool for researchers to speed up their research process without manually grouping by themselves. In fact, there are actually different kinds of classification researchers can use, and each of them works uniquely because their algorithms are built on different concepts. So how does machine learning classification work? It needs training data. So here's the next key concept. Training data is the very first data set that is used to create a machine learning model, and the data you use to train a machine learning model. It works as a guide for the model, and the model sees this data as the rule to follow when grouping new data. So for example, if you are a professional sport player, maybe a tennis player playing a match with another player, how would you know if the ball is going to the right or going to the left during serving? Well, if you have good reaction every time you can react against a 125 miles per hour serve, you're probably the best tennis player. But in reality, this is not the case. As a professional tennis player, you need to study your opponents in order to predict the ball movement. And this is the same thing as machine learning. It needs training data to study and learn in order to be accurate during the classifications with non-training actual data for the research. So it is very important to have a good training data set. Otherwise, the machine learning model or algorithm will not be that effective. And errors are likely to occur, yet researchers need more time to fix the problem. So having a good training data is the very first step to even start the analyzing process. And now we're going to be talk about the number 3 concept, which is decision tree. And a decision tree classification, or DT classification, is the first part of the presentation. It's part of the first presentation classification that I've gone over, but in here is just a short version reminder. It is one of the examples of machine learning classifications. It groups new data by checking if they pass certain requirements, and the requirement can simply be a yes or no test to a very complicated calculation. In reality, a classification can be complicated, but here is an example of a simple decision tree classification example. Assume we have a perfect training data for US address, and now we want to group new US address into 4 groups. Each group represents a region of the US, and each region includes different states. So we have a total of 4 regions: West, Midwest, South, Northeast, and if an address has NY, New York State, in it, it passes the Northeast requirement and matches one of the states, which is New York, and it fails other regions' requirements. So the address with the NY belongs to the Northeast group. On the other hand, if an address has CA in it, which is California, it will pass the West region requirement and fail um, the others. Um, Now we just went over the keywords. Let's get into the article. So the authors continue to introduce different classification and how it works. Here are the remaining classification we will go over with. First, we have RF, or random forest classification. It has many separated decision trees, and each tree will run on its own grouping, and the group with the most tree grouped will be used as the final decision. Here's a picture of a random forest classification with 40 different decision trees. Let's say we are trying to group fruits with apples, oranges, lemons, and bananas, and we know that the fruits that is being analyzed right now is a lemon, but the classifier does not know yet. But in our fruit data sets, there are two fruits that are yellow, which is banana and lemon. So each tree will pass a test on whether the fruit is yellow or not, and definitely it will not pick both apple and orange because they're not yellow, they're red and orange, with the remainder lemon and banana as their choices. And let's say at the end there are 31 trees ended up classifying as lemon and 9 trees ended up classifying as banana. The random forest classification will group the fruits as lemon because the majority of the trees picked the lemon. Then we have boost decision tree classification. It is a model that starts with training data. Then create a second model that fixes the previous model errors until it finally reduces most of the errors. With another examples with the fruit data sets, let's say a tree is 75% accurate grouping lemons, and 25% of the time is wrong. With boosted decision tree, an example will be ADA boost. It will try to minimize the previous errors that were made, and the final tree will be optimized to the point where it is accurate enough to predict lemon for the most part. Next, we have ANNS, or artificial neural network classification. And here's an image of how it works, and is a bit difficult to grasp the concept. So bear with me. And here, for this classification, it has at least 3 layers with an input layer, hidden layer, and output layer with neurons in each layer connected to the adjacent neurons that creates a network. Starting from the input layer, the input layer is assigned into neurons with a random number known as weight, and move on through a channel to neurons in a hidden layer. Same steps applied in the hidden neurons, and move to the output layer and result in outcome for prediction. Because of many neurons are involved, this classification is relatively slow when training. Next, we have KNN, or K nearest neighbor classification, which is it performs differently because it performs grouping by comparing the new data or the unknown data with the training data based on their similarities and how close they are. Here is an example. Blue dots are training data. We have group A in the right corner and group B in the left bottom corner. The red dots represent the new data, and we labeled it as N1 and N2. It is obvious that N1 belongs to group A, and because it is pretty close to the rest of the group A data, but N2 is in the middle. So with KNN model, it creates a range, which is the orange circle. And we can see that within the range, there are three group A data and two group B data. Thus, K nearest neighbor classification concludes that N2 belongs to group A because it is closer to the group in the orange circle, which is group A. As we can see, there are 3 dots, and group B, there's 2 dots. So N2 belongs to group A. So another main discussion of the article talks about which classifiers is the best for researchers to choose. And in fact, every researcher has their own opinions. Some said decision tree is better, and some said random forest is better. Is the reason why they said it because each of their studies works a little bit different and the setup are different. So another study by Lawrence and Moran created a test to figure out which classifier performed better. They kept the setup constant, so each classifiers, and there's no advantage or disadvantage. Everything was kept in constant, and the test used different data sets. And on average, random forest classification performs better compared to other classification. So the authors in this article actually recreated a similar test to see which classifiers perform better using Indian Pines dataset and GeoBia data set. It turns out that SVM classifier, aka support vector machine, a classifier that should have presented from partner presentation video, it outperformed others in Indian Pines dataset, which the highest overall accuracy percentage, while in GeoBia dataset, random forest classifier outperformed the others with the highest overall accuracy percentage. In other words, the best machine learning algorithm does not exist. Researchers need to test multiple classifiers at the same time in order to find out which is the best for their studies. Moreover, there are other reasons can affect a classifier's performance, such as user-defined parameter settings and training data. So what are some training data requirements that is needed to have better performance with the classifier? One argued that the size of the training data is affecting the performance of classifiers. There should be at least 10 or more variables, and it would be better to have 100 variables. Well, at the end, the researchers came up with a conclusion, and based on different studies, a higher sample size of training data leads to better classification accuracy. In fact, studies show that some classifiers are actually sensitive to the training data sample size. Rogan discovered that this when size is reduced by 25%, the accuracy for ANN and decision tree both dropped it by 10% and 35%. Meanwhile, Powell and Moffett added 2,000 more data samples into their studies, and they were using decision trees. So the accuracy of the decision tree classification went up from 78.3% to 84.2%. Another reason why it might affect the accuracy of classification is imbalance class problem. It affects the accuracy of the classification due to a disproportion of the data set. For example, in Indian Pines data from the article, there are only 5 samples of oaks group. To solve such problem, we can simply oversampling oaks or undersampling other large sample groups to keep the groups or classes balanced. On table 6, using random forest classification, the accuracy of oaks is only 0.27 or 27% before balancing. Then the accuracy went up to 0.47 or 47% after balancing the sample size. Thus, class balancing is also another reason that can affect classification accuracy. So the summary for part 2 presentation. Number 1, the best machine learning algorithm does not exist. Researchers need to figure out which classification can perform the best for their studies. Training data can also affect the classification accuracy. Therefore, it is better off for researchers to try to get a large sample training data to improve the classification accuracy. Researchers need to beware of class imbalance problem. This is number 3, and make sure that the proportion of the data set does not happen to ruin the accuracy of the classification. So finally, we reach the end of this presentation. To finish the journal article, please watch part 3 and part 4, which will go over topics such as user-defined parameters, a factor that can cause classification accuracy a little bit off, and the conclusion of the entire journal article. Thanks for watching this presentation and have a good day.